Welcome to the Deep Dive. Today we're tackling a really fascinating and honestly incredibly useful field, statistical pattern recognition and machine learning.
hmm
Think of it like, well, giving computers the ability to find hidden structure and make smart predictions from just mountains of data.
Yeah, huge amounts. And we've got a really rich set of sources here that help unpack the core ideas.
We do.
We've sifted through discussions on everything from how to draw the best curve through some scattered points,
hmm
all the way to really sophisticated methods for understanding sequences like time series and even how to combine different predictive models effectively.
So our goal in this deep dive.
Well, it's really to distill the fundamental principles. We want to reveal some of the surprisingly elegant ways these techniques work, and maybe more importantly, why they actually matter in a practical sense.
And for you listening, the learner, our mission here is to make this clear, engaging, hopefully not too dry.
Right. We won't get bogged down in every single technical detail, but we will aim to give you the essential insights.
Exactly. We'll be exploring ideas like fitting polynomials, the absolute crucial role of probability.
Can't avoid that one.
No. Different types of models like linear models, neural networks.
Cornell methods, too, which are quite clever.
Yeah. And ways to represent complex relationships like graphical models, handling mixtures of data, dealing with uncertainty.
Approximate inference, sampling methods.
Simplifying complex data with dimensionality reduction, understanding sequential patterns, and even how to, get the best results by combining models.
It's a broad field.
It really is. So where should we start? Let's maybe begin with something that seems straightforward, but actually has some real depth-fitting curves to data.
Absolutely. That's a great starting point. Imagine you have a set of data points plotted out. Maybe, I don't know, the relationship between how long you study and your test score, something like that.
Okay, good.
One of the first things you might want to do is just find a curve that sort of follows the trend in those points.
Makes sense.
A common way to do this is by using a polynomial, like a straight line or a quadratic curve or something more complex. The order of the polynomial, often called m, just determines how wiggly or complex that curve can be.
Right. And we see this illustrated, I think it's figure 1.4 in the source material. If you use a really simple polynomial, like just a straight line, m equals 1,
Yeah, m1.
it might completely miss the underlying pattern if it's curved. But then if you crank the order way up, say to m9, the curve can get incredibly complex, super wiggly.
It starts chasing every single data point.
Exactly. It looks like it's literally just memorizing the training data.
And that's a really key observation.
Yeah.
Because while that higher-order polynomial might look like a perfect fit on the data we use to train it, meaning it has almost zero error on that specific set, it can perform terribly, just absolutely terribly, when you show it new data it hasn't seen before.
Okay.
And that's the classic danger of overfitting. The model becomes too specialized.
Too tuned to the noise.
Precisely. Too tuned to the noise and the quirks of the training data, so it fails to generalize to the underlying pattern.
So how do we measure how well the curve is fitting? And crucially, how do we spot this overfitting problem in practice?
Well, we can use a metric called root mean square, or RMS error. It's defined in equation 1.3. Essentially, it calculates the average size of the errors at the difference between the curve's prediction and the actual data point.
Okay.
We square the errors, average them, and then take the square root. Dividing by the number of data points helps compare data sets of different sizes, and the square root gets the error back into the original units, which is handy.
Got it. And does that help us see the overfitting?
Yes, especially when we look at figure 1.5. This plot is really insightful. It shows the RMS error on both the training data and a separate test set data the model hasn't seen during training as we increase the complexity of the M value.
Ah, okay. What do we see there?
Well, notice the training error. It generally keeps going down as M increases. The model gets better and better at fitting the training data.
Right. Makes sense.
But look at the test error. Initially, it also goes down, suggesting a better fit to the real underlying pattern. But then, usually after a certain point, it starts to rise again.
Even while the training error is still dropping.
Exactly. That divergence, that upward turn in the test error, while the training error keeps falling, that's your classic sign of overfitting.
So there's a kind of sweet spot for M.
Precisely. It's not about getting the absolute minimum error on the data you already have. It's about finding that level of complexity somewhere around M3 to ME8 in that specific figure, where the model generalizes best to new unseen data.
Okay. But what if we do go too far? Or what if the best M still seems a bit too complex? How do we actively prevent our models from overfitting?
That's where a really important technique called regularization comes in. Equation 1.4 shows that we add an extra term to our error function.
An extra term, what does it do?
This term adds a penalty based on the size of the model's parameters, the weights. Basically, if the weights in the polynomial get very large, which often corresponds to those very wiggly curves, the
Yeah.
penalty increases.
So it discourages large weights.
Exactly. The penalty strength is controlled by a coefficient, lambda.
Right.
By adding this penalty, we're essentially telling the model, okay, fit the data well, but keep your weights, your coefficients, reasonably small. Don't go crazy.
It's like putting a brake on the complexity. I think the source mentions these are sometimes called shrinkage methods.
That's right, shrinkage methods. And it specifically mentions ridge regression, which uses a squared penalty on the weights.
Okay.
And it points out a connection to something called weight decay in neural networks.
Oh, interesting. So the same core idea pops up in different types of models.
It does. It's a fundamental concept. And really, all this stuff, fitting curves, regularization, it's all fundamentally about dealing with uncertainty in the data and making the best possible predictions despite that uncertainty.
Right. Which logically leads us to.
Probability theory. It's the mathematical language we use for quantifying and manipulating uncertainty. It's absolutely foundational to almost everything in pattern recognition and machine learning.
Okay, let's dive into probability a bit. We had that simple example earlier, picking fruit from different colored boxes. Can you remind us of the core ideas that illustrated?
Sure. We had, say, a red box and a blue box, each with a different mix of apples and oranges. Equations 1.14 and 1.15 just gave us the basic probabilities, like the chance of picking the red box versus the blue box to begin with.
Okay, the overall chance.
Then we talked about conditional probability. That's about how the probability of one thing changes if we know something else has happened. For example, what's the probability of picking an apple, given that we've already chosen the blue box?
Right, and that was just the fraction of apples inside that blue box.
Exactly. It's about how knowing one piece of information, like which box we picked, influences our belief or expectation about something else, like the type of fruit we'll get.
Okay, that makes sense for distinct items like boxes and fruit. But what about things we measure, like temperature or height, that can take on, well, any value within a range? Continuous variables.
Right. For continuous variables, we don't talk about the probability of a single exact value, because that's usually 0. Instead, we use probability densities, often written as px.
Density.
Equation 1.27 shows something interesting and a bit subtle. It shows how these densities transform if we change the variable itself, like switching from meters to feet.
How does that matter?
Well, the peak of the probability density, the value that seems most likely, can actually shift depending on the variable you choose to use. It highlights that our perception of what's most probable can depend on how we represent the data.
Huh, that is subtle. What else?
We also have the cumulative distribution function, PSE, in equation 1.28. That tells you the probability that your variable will be less than or equal to some specific value z.
Okay, like the chance the temperature is below freezing.
Exactly. And when we have multiple continuous variables like temperature and pressure together, we use a joint probability density, px, in equations 1.29 and 1.30 to describe the likelihood of specific combinations of values occurring together.
And for discrete things like counting events.
For discrete variables, like the number of heads in 10 coin flips, we use a probability mass function instead of a density function. It directly gives the probability of each specific count.
Got it. So probability gives us the framework for both discrete and continuous uncertainties. Now, the source also mentions a Bayesian perspective. How is that different from, say, just calculating frequencies?
The Bayesian approach brings in the idea of prior beliefs. Before you even see the data, you might have some initial guess or belief about the parameters of your model, like the coefficients of that polynomial curve we talked about.
Okay, a starting point.
This is represented by a prior probability distribution, like PW, in equation 1.65. This prior might come from previous experiments or just be a general assumption about simplicity, perhaps controlled by things called hyperparameters, like alpha.
And then the data comes in.
Right. Then, as you observe the data, you use Bayes' theorem. This theorem provides a formal way to combine your prior belief with the information from the data, which is captured in the likelihood function, to get an updated belief.
The post.
Exactly, the posterior distribution. This posterior represents what you now believe about the parameters after having seen the evidence from the data. It's a principled way of updating your knowledge.
It feels like starting with an educated guess and then letting the data refine that guess. Very intuitive. Okay, so we've covered curve fitting, probability foundations. But what happens when our data isn't just two variables, but maybe hundreds or thousands? The source mentioned the curse of dimensionality. Sounds ominous.
It is a really significant challenge in practice.
Yeah.
Figure 1.19 uses data from an oil pipeline. It has multiple measurements trying to classify the flow type,
Yeah.
oil, water, or gas mixture.
Okay.
It shows a simplified 2D view. Imagine trying to classify a new data point across in the figure by looking at its nearest neighbors. In 2D, it might seem okay, maybe a bit ambiguous as it has neighbors from different classes nearby.
Yeah, I see points from all three classes close to it.
Now imagine that wasn't 2 dimensions, but 12 or 50 or 500 dimensions. As the number of dimensions or features grows, the volume of that space just explodes exponentially. Yeah. So for any fixed number of data points, they become incredibly spread out in that high-dimensional space. They become very sparse.
Sparse, meaning like mostly empty space between the points.
Exactly. Think about the corners of a cube. In 3D, there are 8 corners. In 10D, there are over 1,000. In Hofstindi, it's astronomical. Your data points effectively live in these distant corners, far from the center and far from each other.
Wow, so finding nearby points becomes much harder.
Much harder. The whole concept of a local neighborhood starts to break down because everything is far away from everything else. This sparsity makes many standard techniques, especially those relying on local information like nearest neighbors, much, much less effective. It's a genuine curse.
Okay, so more data features isn't always better. It can actually make things harder. So given this potentially high-dimensional, uncertain data, how do we actually make decisions? Like assigning a point to a class oil, water, or gas. That's where decision theory fits in, isn't it?
Precisely. Decision theory gives us a formal framework. It combines the probabilities we've been talking about with the costs or losses associated with making different kinds of mistakes.
Ah, so it's not just about being right, but about the consequences of being wrong.
Exactly. It introduces the idea of a loss function. This quantifies how bad it is to make a specific wrong decision, like misclassifying gas as water. Maybe that's more costly than another error. Then we look at the expected loss, which is the average loss we'd expect based on the probabilities and the loss function. The goal is usually to make decisions that minimize this expected loss.
Makes sense. What are the main strategies for making these decisions that the source mentions?
It outlines 3 main approaches: generative models, discriminative models, and discriminant functions.
Okay, what's the difference?
Generative models try to learn the whole process. They model the probability distribution of the data within each class, P and XCK, and also the prior probability of each class, P and HCK. They learn how data for each class is generated.
Okay, building a full picture.
Discriminative models are more direct. They focus just on learning the boundary between the classes. They directly model the conditional probability of the class given the input, PCKX.
So just figuring out where the dividing line is.
Right. And discriminant functions are even more direct. They just learn a function that maps an input X straight to a class label, often without even calculating explicit probabilities along the way.
It sounds like generative models are doing the most work, learning the most detail. What are the trade-offs?
You hit it. Generative models, because they model the full data distribution per class, can be very data hungry, especially in high dimensions. You need a lot of data to estimate those PXCK accurately.
The curse of dimensionality again.
Exactly. But the upside is they can do more things. They can generate new synthetic data points that look like they belong to a class. They can also be good at detecting outliers points that don't look like they belong to any class. Discriminative models are often more efficient for just classification because they focus computation on the decision boundary itself. Discriminant functions are typically the simplest and fastest, but they give you the least insight, just the final decision. Choosing between them depends on the task and the data available.
Right, trade-offs as always. Okay, so we have probability for uncertainty, decision theory for action. The source also brings up information theory and entropy. How does that connect?
Information theory gives us tools to quantify information and, relatedly, uncertainty. Entropy, defined in equation 1.72, is a key measure here. It quantifies the average level of surprise or uncertainty associated with the possible outcomes of a random variable.
Surprise. How does that work?
Well, think about a biased coin that lands heads 99% of the time. Seeing heads isn't very surprising, carries little information. Seeing tails is very surprising, carries a lot of information. Entropy averages this out. A distribution where all outcomes are equally likely, like a fair coin, has the highest entropy, maximum uncertainty.
Ah, I see. The example in the source compares a uniform distribution to a non-uniform one.
Exactly. It shows that a non-uniform distribution, where some outcomes are much more probable than others, has lower entropy. There's less uncertainty overall because you have a better idea of what's likely to happen.
Okay. And there was a link to data compression.
Yeah, that's a fascinating connection. Entropy provides a theoretical lower bound on how much you can compress data. If you know some symbols or events are more probable, you can assign shorter codes to them, like Morse code does for common letters. High entropy means less predictability, therefore harder to compress efficiently.
That's neat. Less uncertainty means more compressible. Okay, let's shift gears to some specific tools used a lot in pattern recognition. The Gaussian distribution is mentioned as being like everywhere. Why is it so ubiquitous?
The Gaussian or normal distribution, especially the multivariate version in equation 2.43, is just incredibly useful and pops up all over the place. It's defined by two key things: the mean vector, which is the center or average location of the data,
The peak of the bell curve.
and the covariance matrix. This
Hmm.
describes the spread or width of the distribution along different directions, and also how the variables change together, their correlation.
Right. Figure 2.7 shows those elliptical contours.
Exactly. In 2D, the shape and orientation of those ellipses of constant probability density are determined entirely by the covariance matrix, specifically its eigenvectors and eigenvalues. It tells you the shape of the data cloud.
So mean is location, covariance is shape and spread. What else makes it so popular?
Well, partly the central limit theorem, which states that if you add up lots of independent random variables, their sum tends towards a Gaussian distribution, regardless of the original distributions. So it arises naturally.
Oh, okay.
Plus, it has really nice mathematical properties.
Hmm.
We mentioned the Bayesian approach earlier. Well, if your prior belief about a parameter is Gaussian, and your likelihood function, how the data depends on the parameter, is also Gaussian, then your posterior belief will also be Gaussian. This is called conjugacy.
Making the math much simpler.
Much simpler. It's a closed-form update. The source also briefly mentions other distributions, like the von Mises distribution for periodic data like wind direction or time of day, where 0 degrees is the same as 360 degrees.
Right, for circular data.
Yeah. And concepts like non-informative priors, which try to express ignorance about a parameter, often get discussed in the context of Gaussians.
Okay, so the Gaussian is a versatile, mathematically convenient default. But what if our data just doesn't look like a bell curve? Or a combination of them? What if it had a really weird shape?
That's where non-parametric density estimation methods come in handy. These methods try to estimate the probability density directly from the data itself without assuming a specific functional form like the Gaussian.
Letting the data speak for itself.
Exactly. The simplest example is a histogram. You just divide the data range into bins and count how many points fall in each bin.
Right, we've all made histograms.
But they have drawbacks. The shape depends heavily on the bin width and placement, and they have sharp edges, discontinuities, which might not be realistic. Kernel density estimators, mentioned in equation 2.249, are a much smoother alternative. The basic idea is you place a small kernel function, often a little Gaussian bump itself, centered on each data point. Then you just sum up all these little bumps.
Ah, so it's like blurring the individual points to see the overall shape.
That's a great way to put it. It gives a smooth estimate of the density. Nearest neighbor methods are another approach, looking at the volume needed to capture a certain number of neighbors around a point to estimate density.
Okay, so ways to estimate density without rigid assumptions. Now let's get back to building predictive models. Linear basis function models for regression. That sounds a bit technical. What's the core idea?
It's actually a very flexible and widely used framework for predicting continuous values regression. The core idea is you take your original input features, x, and you first transform them using a set of fixed functions called basis functions. Let's call them VOX, as in equation 3.2.
These basis functions can be nonlinear?
Yes, they often are. Think polynomials or Gaussians centered at different points or sigmoids. Then the model itself predicts the output as a simple linear combination of these transformed features. So yxw is just sum over j of wjx dx.
Ah, I see. So the basis functions handle the nonlinearity, but the model is still linear with respect to the weights, the w's.
Precisely. And that linearity in the weights makes finding the best weights much easier mathematically.
How do we find those best weights, the w's?
The most common way is the method of least squares, as shown in equation 3.18. You find the weights w that minimize the sum of the square differences between your model's predictions, yx, w, and the actual target values in your training data.
Minimizing the squared error.
Right. Figure 3.2 gives a nice geometric picture. It's like projecting the vector of target values onto the subspace spanned by the vectors of the basis function values. The source also mentions sequential learning, or online algorithms, which are useful for huge data sets where you update the weights one data point at a time.
Okay. And I bet regularization comes up here too.
Absolutely. Just like with the polynomial fitting, we can add a regularization term to the least squares error function, as in equation 3.27, to penalize large weights and prevent overfitting, especially if we have many basis functions. Figure 3.3 shows different types of penalties, like the L1 norm, lasso, which encourages sparsity.
It really is a recurring theme. What about the Bayesian approach to these models?
Yep, we can do that too. Equation 3.31 shows how we can place a prior probability distribution over the weights W, maybe assuming they are drawn from a Gaussian.
Our prior belief again.
Right.
Yeah.
Then we combine this with the likelihood of the data given the weights, and we get a posterior distribution over W. This doesn't just give us a single best W, but a whole distribution reflecting our uncertainty about the weights.
Which seems potentially more informative.
It can be. The source also discusses the bias variance decomposition in this context, a way to understand the trade-off. High bias means the model is too simple and underfits. High variance means it's too complex and overfits the training noise.
Finding that balance.
Exactly. And it shows examples using Gaussian basis functions, illustrating how the posterior uncertainty shrinks and the predicted distribution gets sharper as more data comes in. It also introduces the concept of equivalent kernels, equation 3.62, showing that these linear basis function models often act like weighted averages of nearby training points.
So even these explicit basis function models have an implicit local averaging feel.
Often, yes. The shape of that equivalent kernel tells you how the influence of training points spreads out. And finally, it touches on the Bayesian evidence framework for model selection, helping choose the right basis functions or the right amount of regularization.
Okay, a very powerful framework. Now that was for regression, predicting numbers. What about classification, putting things into categories using linear models?
Right, linear models for classification.
Hmm.
The goal here is usually to find decision boundaries that are linear lines in 2D, planes in 3D, hyperplanes in higher dimensions to separate the data points belonging to different classes.
Drawing lines between the groups.
Pretty much. If you have more than two classes, say K classes, there are different strategies. You could train K1 versus the rest classifiers or KK1-2 1 versus 1 classifiers, or, as in equation 4.9, you can define K-linear functions and assign a point to the class whose function gives the highest output.
And these linear boundaries create specific regions.
Yes, figure 4.3 shows that these linear decision boundaries always result in decision regions that are convex. If the data can be perfectly separated by such a linear boundary, we say it's linearly separable.
But often it's not perfectly separable, right?
Often not. The source introduces Fisher's linear discriminant. This is a dimensionality reduction technique, specifically for classification. It finds a direction to project the data onto such that the projected class means are well separated, while the within-class variance is kept small. It's about finding the most discriminative 1D view, even if classes overlap.
Maximizing class separation. Okay, what about probabilistic approaches?
We can build probabilistic generative models. For instance, assume the data within each class follows a Gaussian distribution, as in equation 4.71. We model PUKK and PCK, then use Bayes' theorem to find the posterior probability, PCKX, for classification.
Okay, modeling each class's distribution.
Or we can use discriminative probabilistic models. Logistic regression is a prime example here. It directly models the posterior probability, PC1x, using the logistic sigmoid function, that S-shaped curve from equation 4.59, applied to a linear function of x.
The sigmoid squashes the output between 0 and 1 like a probability.
Exactly. We usually find the parameters using maximum likelihood estimation. But, the source warns, if the data is linearly separable, standard maximum likelihood for logistic regression can lead to overfitting the weights, can go to infinity trying to make the separation perfect. Regularization is often needed.
Ah, good point. How is it fitted?
Often using an algorithm called iterative reweighted least squares, or IRLS. And for multiple classes, logistic regression can be extended using the softmax function, equation 4.104, instead of the sigmoid. Probit regression, equation 4.114, is mentioned as a similar alternative using a different type of function.
So linear methods can be quite versatile, even probabilistic ones like logistic regression, but reality is often nonlinear. That brings us to neural networks.
Absolutely. Neural networks are really designed from the ground up to model complex nonlinear relationships. A basic feed-forward network, like the two-layer one in figure 5.1, has an input layer, one or more hidden layers, and an output layer.
Connected by weights.
Connected by weights, yes. The key is that the neurons, especially in the hidden and output layers, apply a nonlinear activation function like the sigmoid we just mentioned,
Yeah.
or others like tan or ReLU, to the weighted sum of their inputs. That nonlinearity is crucial.
Without it, it would just be a linear model, right?
Yeah, exactly. No matter how many layers you stack, if you only have linear activations, the whole thing collapses back to a single linear transformation. The nonlinearity allows them to approximate arbitrarily complex functions. Figure 5.2 shows more general topologies are possible, even with skip layer connections.
And they can do regression, too.
Oh, yes. For regression, you might use a sum of squares error function at the output, and maybe just a linear activation function on the output neuron itself if the target value isn't restricted.
Okay, so how do they learn? How do we find all those weights? There can be thousands, even millions.
The workhorse algorithm is backpropagation. Equations 5.56 and 5.57 show the core idea. It's essentially an efficient way to apply the chain rule of calculus to compute the gradient, the derivative of the error function, with respect to every single weight in the network.
Calculating how much each weight contributes to the error.
Precisely. Once you have those gradients, you can use optimization algorithms like stochastic gradient descent, SGD, or its variants, atom, RMS prop, to iteratively adjust the weights in the direction that reduces the error.
Learning by small adjustments based on the error gradient.
Right. But neural nets are powerful, and with great power comes...
Great risk of overfitting.
You got it. Figure 5.9 clearly shows this. Training a network on some simple sinusoidal data, adding more hidden units makes the fit better initially, but too many hidden units leads to wild oscillations that fit the training noise perfectly, but generalize poorly.
So regularization again.
Definitely. Weight decay, mentioned in equation 5.112, is basically the same L2 regularization, like ridge regression we saw earlier, applied to the network weights. Early stopping is another common technique. You monitor performance on a separate validation set, data not used for training gradient updates, and stop training when the validation error starts to increase, even if the training error is still decreasing, figure 5.3.
Stop before it gets too specialized. Makes sense.
The source also touches on more advanced topics like tangent propagation for encouraging invariants to input transformations, convolutional neural networks, CNNs, which are massively successful in image recognition and use clever weight sharing ideas, figure 5.14.
CNNs, yeah, I hear about those all the time.
And even Bayesian neural networks, which try to put probability distributions over the weights themselves, often using approximations like a Gaussian, equation 5.165, to represent the posterior uncertainty. Hyperparameter optimization using evidence framework is also mentioned.
Wow, okay. Neural networks are clearly a huge area. What about kernel methods? You said they were clever. How do they handle nonlinearity differently?
Kernel methods are indeed quite elegant. They offer another way to get nonlinear decision boundaries, but often by extending linear models in a smart way. The central idea is the kernel function, kx XORO, in equation 6.1.
Okay, what does this function do?
Conceptually, it measures the similarity between two input points x and xori. But the trick is, this kernel function often corresponds to calculating the dot product between the points after they've been mapped into some potentially very high-dimensional feature space by a nonlinear transformation.
So you map the data to a higher dimension where maybe it becomes linearly separable.
Exactly. Yeah. But here's the clever part, the kernel trick. You never actually have to compute the coordinates in that high-dimensional feature space. You only need to be able to compute the kernel function, kx XORO, using the original inputs.
Ah, so you get the benefit of the high-dimensional space without the computational cost of working there directly.
Precisely. If your linear algorithm can be expressed purely in terms of dot products between data points, you can replace those dot products with the kernel function, and voila, you've implicitly created a nonlinear version of your algorithm.
That is clever. What are some common kernel functions?
The source lists several in equations 6.19 to 6.22. There are polynomial kernels, Gaussian kernels, also called RBF kernels, very popular, and sigmoidal kernels. Radial basis function RBF networks, equation 6.26, are closely related, using basis functions that depend on the distance to certain center points. Gaussian processes, mentioned briefly, are a fully Bayesian approach that uses kernels to define a prior over functions themselves, equation 6.60.
Okay, so kernels give us nonlinear power by implicitly working in a different feature space. Now, within this area, we have sparse kernel machines. What's the sparse part about?
Sparsity here means that the final model solution depends only on a small subset of the training data points. Support vector machines, SVMs, are the classic example.
SVMs, right, heard of those too.
SVMs, as shown in figure 7.1, are designed as maximum margin classifiers. For separable data, they find the unique hyperplane, line, plane, etc., that separates the classes with the largest possible margin or gap between the hyperplane and the closest points from either class.
Maximizing the buffer zone.
Exactly. Those closest points that define the margin are called the support vectors. The decision boundary depends only on these support vectors.
And if the data isn't perfectly separable,
Then SVMs introduce slack variables, ag in equation 7.19. These allow some points to be within the margin, or even on the wrong side of the hyperplane, but they incur a penalty in the optimization. The trade-off between maximizing the margin and minimizing the penalty is controlled by a parameter, often called C.
so it allows for some errors. Then how are the support vectors found?
So a constrained optimization problem, often solved using its dual formulation involving Lagrange multipliers, equation 7.22. The solution naturally identifies the support vectors. They are the points with non-zero Lagrange multipliers. And importantly, SVMs can be kernelized, equation 7.54. You just replace the dot products in the algorithm with a kernel function.
So you get nonlinear SVMs using the kernel trick.
Yep, nonlinear classification with maximum margin properties. The source also briefly mentions support vector regression, SVR, for predicting continuous values, and introduces relevance vector machines, RVMs.
RVMs, how are they different?
RVMs are a probabilistic Bayesian take on sparse kernel models. They often produce solutions that are even sparser than SVMs, meaning they rely on fewer support vectors or relevance vectors, as illustrated in figure 7.2. They also provide probabilistic outputs.
Interesting. So sparsity means efficiency and potentially better generalization by relying only on key data points. Okay, let's shift perspective again. How do we represent the web of relationships between many variables? Graphical models seem designed for this.
They are. Graphical models use the language of graphs, nodes, and edges to represent probability distributions over a whole set of variables. Nodes represent the random variables, and the edges between them represent probabilistic dependencies.
A picture of the dependencies.
Exactly. They provide a visual way to understand the structure of a complex distribution and a framework for efficient computation. The structure encodes conditional independence assumptions based on the fundamental product rule of probability, equations 8.1, 8.2.
Are there different kinds of graphs?
Yes, two main types. Directed graphical models, also called Bayesian networks, like in figure 8.2, use directed arrows. An arrow from A to B typically means A directly influences B, representing causal relationships or conditional dependencies. Undirected graphical models, or Markov random fields, use undirected edges, representing correlations or symmetric dependencies.
And even simple models fit this.
Oh yes, figure 8.7 shows how polynomial regression can be drawn as a simple, directed graphical model. The source also mentions factor graphs, figure 8.45, which are another bipartite graph representation that can be useful, especially for inference.
So the graph structure tells us who depends on whom. How do we use these models? For inference.
Right. Inference means computing probabilities of interest, like the probability of some hidden variables given the observed ones. For certain graph structures, like trees, there are very efficient exact inference algorithms, like the sum product algorithm, which involves passing messages along the edges of the graph. For more complex graphs with loops, exact inference can become intractable.
Which probably leads us to needing approximations later. But first, what if our data seems to come from several different underlying sources or groups? Mixture models.
Exactly. Mixture models are designed for situations where the overall data distribution seems to be composed of several simpler component distributions. Think of modeling the heights of a population that contains both children and adults. You might use a mixture of two Gaussian distributions.
Combining simple shapes to make a complex one.
Precisely. We often introduce a discrete latent variable, say z, for each data point, indicating which component distribution generated that point. K means clustering, equation 9.1. A popular algorithm for finding clusters in data is actually closely related to fitting a mixture model, specifically a Gaussian mixture, under certain simplifying assumptions. It's an iterative process.
K means, okay, and Gaussian mixtures are common.
Very common. Equation 9.12 defines a Gaussian mixture model explicitly using latent variables, equation 9.11, to indicate component membership. The goal is typically to maximize the likelihood of observing the data under this mixture model, whose log likelihood is given in equation 9.14.
But those latent variables, we don't know which component generated each point.
Exactly. That's the tricky part. That's where the expectation maximization EM algorithm comes in. It's a powerful, general, iterative algorithm, equations 9.47, 9.51, for finding maximum likelihood estimates in models with latent variables.
How does EM work, roughly?
It alternates between two steps. The E step expectation, given the current model parameters. Calculate the expected values of the latent variables, essentially, the probability that each data point belongs to each component. The M step, maximization. Update the model parameters like the means and covariances of the Gaussians and their mixing proportions to maximize the likelihood using those expected latent variable assignments from the E step. You repeat E, R, E, M.
Until it converges. Clever. So mixture models handle data composed of different subgroups. Now, you mentioned inference and graphical models can be intractable, and EM deals with hidden variables. What happens when things get really messy and exact calculation is just impossible?
That's when we need approximate inference techniques. When the exact posterior distribution or marginal likelihood is too hard to compute, we resort to methods that find an approximation.
Like what?
Variational inference, or variational Bayes, is a major one. The core idea is to choose a family of simpler, tractable distributions, say, factorized distributions, and then find the member of that family that is closest to the true, intractable posterior distribution. Closest is usually measured by minimizing the Kullback-Leibler KL divergence.
Finding the best possible simple approximation.
Right. This often involves optimizing a lower bound on the marginal likelihood or evidence of the model, sometimes called the ELBO, evidence lower bound, as shown in equation 10.3. The source shows how this can be applied to mixtures of Gaussians or even variational linear regression. Expectation propagation, EP, is another related powerful technique for approximate inference that's mentioned.
So we trade exactness for tractability by finding a good approximation. What about another approach, maybe drawing samples instead of calculating distributions, sampling methods?
Exactly. Sampling methods, often called Monte Carlo methods, provide a different route to dealing with complex distributions. Instead of trying to calculate the distribution analytically, we generate random samples from that distribution.
How does that help?
If you can draw enough representative samples, you can approximate quantities of interest, like expected values, just by averaging over the samples. The challenge is drawing samples efficiently from complex, high-dimensional distributions.
What are some ways to draw samples?
Basic techniques include rejection sampling, equation 11.14, where you sample from a simpler proposal distribution and accept reject based on a ratio, and importance sampling, equation 11.26, figure 11.8, where you sample from a proposal but weight the samples to correct for the mismatch.
Okay, but maybe inefficient.
They can be, especially in high dimensions. That's where Markov chain Monte Carlo MCMC methods come in. These methods construct a Markov chain, a sequence of random samples, where the next sample depends only on the current one, whose long-run stationary distribution is the target distribution we want to sample from.
So you run the chain long enough and the samples start looking like they came from the target distribution.
That's the idea. Popular MCMC algorithms include the Metropolis-Hastings algorithm, equation 11.45, figure 11.10, which involves proposing a move and accepting it based on a probability ratio, and give sampling, which samples each variable conditionally on the current values of the others. Hybrid Monte Carlo, which uses gradient information, is also mentioned.
Okay, so MCMC gives us powerful tools to sample from tough distributions. Now let's swing back to that curse of dimensionality. We need ways to simplify high D data. Dimensionality reduction.
Yes, exactly. These techniques aim to find a lower dimensional representation of the data that captures the essential structure or variance, making it easier to visualize, process, or build models on.
What's the classic method?
Principal component analysis, PCA, is the cornerstone. It's a linear technique that finds a new set of coordinate axes called principal components, such that the variance of the data projected onto these axes is maximized. Equation 12.16 shows the formulation, often involving eigenvalue decomposition of the covariance matrix. Figure 12.3 gives a visual.
Finding the directions of
Components that capture most of the variance, effectively projecting the data onto a lower dimensional subspace. Probabilistic PCA provides a generative, probabilistic view of the same idea.
But PCA is linear. What if the important structure is curved?
Then we need nonlinear dimensionality reduction. Kernel PCA, equation 12.82, uses the kernel trick we discussed earlier to implicitly perform PCA in a high-dimensional feature space, effectively finding nonlinear structures. Autoencoders are another powerful approach.
Autoencoders, aren't they neural networks?
Yes. An autoencoder is typically a feed-forward neural network trained to do a specific task. Reconstruct its input at the output layer. Equation 12.91. The key is that it has a bottleneck hidden layer with fewer neurons than the input-output layers. Figure 12.19.
Forcing the network to compress the information.
Exactly. To reconstruct the input accurately, the network must learn a compressed representation, a low-dimensional code, in that bottleneck layer. The encoder part maps input to the code. The decoder maps code back to the input. The learned code is your nonlinear dimensionality reduction.
Very clever use of neural nets. Okay, so we can simplify complex data. What about data that arrives over time? Sequential data.
Right, modeling sequences or time series requires different tools than looking at independent data points. Hidden Markov models, HMMs, shown in Figure 13.6, are a classic choice.
HMMs, what's the core idea?
HMMs assume there's an underlying sequence of unobserved hidden states that evolve over time, according to the Markov property, meaning the next state depends only on the current state. Equations 13.1, 13.5. Then each hidden state generates an observable output symbol or measurement.
Like the hidden state is the true condition and the observation is noisy evidence.
Exactly. Think speech recognition. Hidden states are the phones being spoken. Observations are the noisy audio features. Inference in HMMs involves figuring out things like the probability of a hidden state sequence given the observations. The forward-backward algorithm, equations 13.36, 13.44, does this efficiently.
And finding the single most likely sequence.
That's done using the Viterbi algorithm, equation 13.70. The source also mentions linear dynamical systems, like Kalman filters for continuous state spaces, and particle filters, figure 13.23, for handling nonlinear, non-Gaussian sequential models, which are much harder.
So specialized models for data where order matters. Finally, the last major topic is combining models. Why not just find the single best model?
Sometimes, combining the predictions of several different models in ensemble can lead to better, more robust performance than any single model could achieve on its own. It's like asking a committee instead of just one expert.
Averaging out errors?
Partly, yes. Simple committee methods just train multiple models, maybe on different subsets of data or with different initializations, and average their predictions. Boosting is a more sophisticated sequential approach.
How does boosting work?
In boosting, equation 14.23 shows an example, you train models sequentially. Each new model is trained to pay more attention to the data points that the previous models got wrong. It focuses on the hard examples. The final prediction is a weighted combination of all the models.
Learning from mistakes. Interesting. What else?
Decision trees, figure 14.4, are mentioned. These are hierarchical models that make predictions by asking a sequence of simple questions, like following branches down a tree. Individual trees can be weak, but combining many trees, like in random forests or gradient-boosted trees, is extremely powerful. Mixture of experts is another idea where you have several expert models and a gating network learns which expert is best for different parts of the input space.
So, leveraging the wisdom of crowds or specialized experts. Now, to wrap this all up, the source revisits that oil flow data as a case study. What's the takeaway?
That oil, water, and gas pipeline dataset, Appendix A, Figure 8.3, is a good reminder of real-world complexity. You have high-dimensional sensor readings, and the goal is to distinguish between different flow patterns, homogeneous, annular, laminar. These patterns are physically distinct, but might look similar in the raw data, with complex nonlinear relationships between the sensor readings and the flow type.
So it's a real test case.
Exactly. It really underscores why we need the kinds of techniques we've discussed. Simple linear models likely wouldn't cut it. You need methods that can handle high dimensionality, addressing the curse, capture nonlinearities like neural nets or kernel methods, maybe even model sequential dependencies if looking at data over time, and robustly classify between complex patterns. It ties together the need for this whole pattern recognition toolkit.
It really does. It drives home that analyzing complex, real-world data effectively requires understanding these diverse concepts and methods. Okay, so to try and summarize this, whirlwind tour.
It was a lot.
It was. We've journeyed through the core ideas of statistical pattern recognition, machine learning. We saw how probability is the bedrock for handling uncertainty, how decision theory helps us act on those probabilities, considering costs, and the sheer variety of models from linear approaches, basis functions, all the way to neural networks, kernel methods.
Graphical models for dependencies, mixture models for heterogeneity.
Right. And tackling challenges like high dimensions with PCA or autoencoders, handling sequences with HMMs, and even improving performance by combining models.
And what's really striking, I think, is how interconnected these ideas are. You see regularization pop up everywhere. Kernels bridge linear and nonlinear worlds. The Bayesian framework offers this consistent lens for thinking about learning and uncertainty across many model types.
It's not just a random collection of tricks. There are deep principles connecting them. It's been a really fascinating exploration. And for anyone listening who wants to make sense of data, which is pretty much everyone these days,
Wait,
understanding these fundamentals is just, well, essential. For me, maybe the biggest aha moment was seeing those connections, how something like regularization isn't just for one model type, but a general principle.
yeah, seeing the underlying unity is really powerful.
So, to leave our listeners with something to chew on, a final thought.
Well, we've covered a lot of powerful tools, many developed over decades, but data today is getting even bigger, faster, more complex real-time streams, unstructured data. So looking ahead, what are the next frontiers? Will we need fundamentally new types of pattern recognition approaches to emerge? Or will the big breakthroughs come from more clever combinations, scaling, and refinements of the core principles we've talked about today?
That's a great question. Are we building on the foundation or do we need a new one? Something to definitely ponder. Thank you for joining us on this deep dive. We really hope it's given you a solid grounding and maybe spark some curiosity to explore this incredibly dynamic and vital field even further.